Up until now in our discussion on pH, you would be given a hydronium or a hydroxide concentration. So now what we want to do is we want to start to look at the more simple examples whenever you're given a strong acid and a strong base and you are actually deriving the concentration of the hydronium ion or the hydroxide ion. So one of the first things is to consider that whenever we're looking at a strong acid or a strong base, there's 100% dissociation, or at least that's what we assume. So what that means is if we were to start off with something that was like a 1 molar solution of HCl, so hydrochloric acid, this would be our initial concentration. What would happen is, because this is dissociating nearly 100%, that means that at equilibrium, that H plus concentration would be 1 molar, and then that Cl minus concentration would also be 1 molar. So we'll do a few numerical examples as we look at this, but what this means is if you have a monoprotic acid, so mono means 1, protic means proton. So if we have an acid with 1 proton and it's a strong acid, we will assume that it dissociates 100%. We might see diprotic acids and other polyprotic acids later on as we go. But right now the focus for today's lecture is just looking at monoprotic acids. We'll also start to look at some strong bases. And so for us, a strong base will be some sort of alkali or alkaline metal with hydroxide. And what we'll see is whenever you dissolve this solid in water, it will give an aqueous solution, and then that dissociates completely into the metal cation and then hydroxide. So we'll look at a few examples as to how you can get the concentration of hydroxide from this. So our first example, we'll be looking at calculating the pH of a strong acidic solution. So here you have nitric acid, HNO3, and nitric acid is a strong acid. So this means we're assuming complete dissociation. So if this thing dissociates completely, it's going to break up into two parts. It's going to break up into H+, which will go on to form hydronium, and it's also going to break up into nitrate. So what that means is the concentration of hydronium over here, because it's dissociating completely, will be 0.025 molar. And the same thing for nitrate. Our nitrate concentration would be 0.025 molar. So if we want to find the pH of this strong acid, we'll just use our equation. pH is equal to negative log of the concentration of hydronium. And we'll plug this in. So negative log of 0.025 molar. Whenever we plug this in, we'll get a pH of 1.6. And so this will be true for all strong acids that are monoprotic. Let's go ahead and look at some strong bases. So whenever we look at strong bases, again, we're going to assume that they dissociate 100%. And so here, for sodium hydroxide, it would dissociate into sodium ions and hydroxide ions. And in this case, the concentration of both the sodium and the hydroxide ions would be 0.10 molar, because this solution, the sodium hydroxide, dissociates completely. So if we want to find the pH, given what we start with, the concentration, I would actually find the pOH first. If you want to use kW, that's fine, but this is just one way to do it. I would say find the pOH first. So pOH is equal to negative log of OH minus. Plugging in, we'd have negative log of 0.10 molar. Okay, so we'll plug this in and we'll have pOH is equal to 1. We'll recall that pH plus pOH is equal to 14. So if we're asked to find pH, we'll just take 14 minus the pOH, which in this case pH would be equal to 13. So this is a basic solution. The next example is one that is very easy to make a mistake on, especially on an exam whenever you're in a hurry. So here we have a 0.0050 molar solution of slaked lime, and we want to find the pH of this solution. So you're thinking, strong acid, strong base. So, okay, since there's hydroxide, that must mean the concentration of Ca2 plus would be equal to the concentration of OH minus, and that these concentrations would be equal to the initial concentration, 0.0050 molar. Well, that is actually incorrect, because in this case, notice that there are two hydroxides. So the concentration of the hydroxide is actually going to be equal to double that of the calcium, or double that of the initial calcium hydroxide solution. So we'll have 2 times 0.0050 molar. So our initial concentration of hydroxide is 0.010 molar. And now we can just go ahead and plug in and find the pOH. So this equals 2. And if the pOH is equal to 2, we'll use this relationship up here again, that pH plus pOH is equal to 14. So the pH is equal to 12. So watch for strong bases whenever there's 2 or more hydroxides. I don't think you'll ever see anything really with more than 3. 2 is the most common that you would see. And so finally, let's go ahead and look at one last example of calculating the pH of a strong base. So in this case, we're going to have to use a few more skills other than just using pOH is equal to negative log of the hydroxide concentration. In this particular example, it tells you how the lime water is made. So in this case, you start with 0.28 grams of lime, the calcium oxide, and enough water to make 1 liter of lime water, which is the calcium hydroxide. So what we need to do is we need to write a balanced chemical equation. So we know that we have this calcium oxide plus water, and it goes on to form calcium hydroxide, that lime water. So if we want to find the pH, eventually we're going to have to find probably the concentration of OH minus is what I would be looking for. So then once we know that concentration in a roundabout way, we can end up getting the pH. So, but all we're given is this initial mass of this solid here, and then the volume that it's diluted to. So let's go ahead and start with what we know, which is our mass. So we have 0.28 grams of calcium oxide. And if we want to compare that to our product over here, we need to use a mole-to-mole ratio. So that means let's go ahead and convert this from grams to moles. So we have 1 mole of calcium oxide. The molecular weight of that is 56.08 grams of calcium oxide. The mole-to-mole ratio is 1 mole of CaOH2 for every 1 mole CaO. And when we plug that in, we'll get 0.0050 moles of calcium hydroxide. So we can go from moles to molarity pretty easily here, since we have 1 liter, because recall that molarity is moles per liter, so we're just dividing by 1. So here's the tricky part, yet again, is notice that this is 2 hydroxides present. So if we want to find the concentration of OH minus, we'll take 2 times that concentration of the calcium hydroxide. And so then we'll end up with a concentration of 0.010 molar. We can find the pOH. Which is equal to 2. So pH would be equal to 14 minus the pOH. So our pH is 12. So that's how you would deal with strong acids and strong bases and finding their pH or POH or their hydronium or hydroxide concentrations. As we go on, we'll start to look at having to use equilibrium constants and ice charts to calculate pH and POH for weak acids and weak bases.